Okay, so in today's lecture, what we will do is that we will look at how to use the Raspberry Pi as a hardware controlling unit. We will begin in this chapter looking at the hardware basics. The first thing that we need to know is that there is a connector on the Raspberry Pi that we can then use to hook up wires into other devices, other hardware devices, for example, like other lights or motors or sensors and so on. So these connectors together are referred to as the GPIO pinout of the Raspberry Pi. The GPIO stands for General Purpose Inputs and Outputs, and the pinout just gives you every pin and the name of that pin so that you can understand its functionality. For example, we know that this pin here can supply 5 volts. This pin can supply 5 volts. This pin can be used to supply 3.3 volts. The pins that I have numbers like 23, 24, 22 can be programmed to be digital input or digital output. Digital input, it means that we can check if something is on or off. Digital output, it means we can make something on or off. For example, we can turn a light on or we can turn it off. So we can program these pins like 23, 24, 22 to be either of these things. Ground is the connection that we will use in order to complete the circuit. So for example, if we were powering a LED, then we would be connecting from 5 volts into the resistor and then an LED and then back to the ground. We always have to bring the signal back to the ground. There is a combination of lines that can be used to connect other Raspberry Pis or other microcontrollers or other devices serially. For example, a group of these pins is what we have here, SDA and SCL. These pins can be connected, for example, between two different Raspberry Pi. So I will connect the SDA to SDA and SCL to SCL. Excuse me. And then I can use this connection in order to communicate between the two Raspberry Pis. Here, for instance, I have the TXD and the RXD. These are also used for serial connection. So if I can connect the TXD from here to the RXD from here, and then the TXD from here to the RXD from here, then I would have a connection that would allow me to communicate between the two Raspberry Pi. It doesn't have to be two Raspberry Pis that I communicate between. It could be a Raspberry Pi and then some other module, for example, like a laser module. The laser module will allow me, for example, to have laser related functionality without actually having to go and understand the circuitry of this. So how would I then control it? You control it by talking to it serially, and you send it bits one by one. That's what it means to have serial communication. We send the bits one by one. There is a protocol for how this exchange will happen, and these are the implementation of these protocols. There is another one here which we call SPI, which have pins like master output slave input or master input slave output or slave clock. Or we also have any of the pins can be used as a slave select. So this is called SPI. This group of pins are called SPI. Again, they're used to communicate between different Raspberry Pi and microcontrollers serially, as in one bit at a time. These pins are called I2C. Again, they serve the same purpose. And then these pins are called serial. They also serve the same purpose. This is the GPIO pin out of the 40 pin models of the Raspberry Pi. You will notice here that what we have is that we have more pins, more ground connections, but it's the same idea. Here we have the serial pins for serial or USART. We call this USART. Or here we have the I2C serial communication pins, and here we have the SPI serial communication pins. And then we have a lot of pins that can be programmed as GPIO input or GPIO output. Notice that the Raspberry Pi does not have analog inputs, nor does it have analog outputs, but we can still do those by programming these pins in certain ways. We'll see that as we progress through the chapter. This is called a hat for the Raspberry Pi. It sits on the place of the GPIO connectors and then provides additional functionality. Here, the simple functionality it provides simply is giving you the name of every pin, so that when you make connections, you make connections in the right place. So for instance, if we do not have this hat in here, then you would see these pins and you'd have to count all the way to find the pin that you want. Here we don't want to do this counting thing. We can just put it, and then if we want to make a connection to RXD, we can simply take the connection from here or take the connection from there. Now, it is important that when we make connection to the Raspberry Pi, that we keep certain principles that are there to safeguard the Raspberry Pi from any damage. So we do not connect more than 3.3 volts on any GPIO pin if I'm using it as an input. If I'm using the GPIO pin as an input, then the maximum voltage that this input line should see is 3.3 volts. We also do not draw more than 16 milliampere per output and keep the total of all of the outputs 50 milliampere for the older versions of the Raspberry Pi and 100 milliampere. So this means what? This means if I am going to be connecting the Raspberry Pi so that it can power certain things, like for example power an LED, I need to make sure that this LED will not draw more than 16 milliampere to function from that one pin. So for instance, here I have these pins, for example, like 7 and 8 and 16 and 20 and 21. I need to make sure. How do I make sure? I look at the data sheet of whatever thing I want to connect, and then I see how much current it will draw. If it's going to be drawing more than 16 milliampere, I should not be connecting it. Okay. Not only this, every pin can supply maximum of that amount, but in total, everything that I connect to the Raspberry Pi need not to exceed the 100 milliampere. So this is this is the second principle of this, is that the total for all outputs should not exceed the 100 milliampere. Now, when I use LEDs, 3 milliampere is enough to light a red LED. Okay, so this just gives you an idea, is that I cannot draw more than 16 milliampere from an LED, but all what it needs is 3 milliampere. So this is kind of like a maximum there. Now, we do not poke the GPIO connector with a screwdriver, because if I have a screwdriver and the screwdriver will then form a circuit between two different pins because it's metal, then that would lead into a short circuit and that can damage the Raspberry Pi. Also, we should not power the Raspberry Pi with more than 5 volts. Okay, so we should not expect to power anything from the Raspberry Pi with more than 3.3 volt if we are controlling it. We can still use the 5 volt in order to power something that is 5 volts, but we should not connect to the input line more than 3.3 volts. And also, the Raspberry Pi should not be powered by more than 5 volts. Now, we do have 5 volt supplies that we can use to power things. The maximum we can draw from these supplies is 250 milliampere. We should not be drawing more. Now, remember, what's the difference between the 100 milliampere that we can draw from here and the 250 milliampere that we can draw from here? If we look at the Raspberry Pi, we'll find that there are two pins that are labeled 5 volts, 5 volts. From these collectively, I should not be drawing more than 250 milliampere. Now, however, from these pins 18 and 23 and 24 and 25 and 8 and 7, from these GPIO pins, I should not be drawing more than a collective 100 milliampere and each 16 milliampere. Now, we often require to connect the Raspberry Pi to some other external devices and then communicate between them, and we discussed a number of serial protocols that can help us do this. One protocol is the I2C protocol. So in the I2C protocol, we first need to set it up. So what we do in order to set it up is that we start the command rasbconfig. Okay, how do we start that command rasbconfig? We simply say sudo rasbconfig from a terminal, and then depending on whether we have the Raspberry Pi in desktop mode or whether it's in the command line mode, one of these things will pop up. That will allow me to go to the I2C, and then if it's disabled, I can go and I enable it. The same thing for the SPI and the serial. These are the three protocols that are there to communicate with the Raspberry Pi over wires, over simple wires. And I can enable whichever one I want from there. That also allows me to enable SSH and camera if I need to. So that's the step number one. That's how you enable these systems. Now, what kind of modules you can go ahead and step number two, you need to download and install the library, and that can be done using the sudo apt-get install python smb us smbus. So once you do this, then the library that is needed for the I2C will be there available for us to then go and use within our Python code. Once you're done with this, once you enable it and then you install the library, then what you have is you have a bunch of different things that you can then hook up to your Raspberry Pi through I2C. For example, this is a servo motor controller, allow you to control 16 servos directly. This is 7 segment displays that allow you to display numbers there for a human to, let's say, for example, know what time it is or what temperature it is. This is a real-time clock that will tell you what's the current time, the correct time, so it's like a small watch. This is an LED matrix that will allow you to draw on that matrix to show something to the user. So all of these, require I2C for communication. Now, how does I2C work? I2C typically work by assigning an address to each one of these devices that you connect to the I2C. That means you can really connect multiple devices into the I2C pins. But, each device in this case now will be taking an address, and then you can direct your messages to a particular device by using this address. In order to find out what this address is for the different devices that are connected, first you install the I2C tools, so sudo apt-get install I2C tools, and then there's this command which is I2C detect -y1 with sudo because it requires hardware access. Once you do this, you're going to be getting something like that. And in this output, you will notice that there are two things here that are non-dashes, or there are entries. One is where 60 meets 8, so which is 68, and the other one is where 70 meets 0, which is the 70. So we know now that there are two devices connected to the I2C pins, and these are their addresses. Now, SPI, that's another protocol that we use. Again, how do we get it to work? First, we, of course, now as you see, we have not seen how to use the I2C within Python code. That comes in later. As you can see here, there are recipes that use I2C later on. So we now just need to know how to set it up and configure it. Now for SPI, sudo raspberry config will then take you to that screen where you enable and disable the different protocols, and then you can go ahead and enable it if you want. Now, the one code which we will see here in this chapter related to serial communication is for the USART, or the last protocol for serial communication, what we call the serial protocol. To do use it in a code, then you need to install PySerial. So to install PySerial, you run the command sudo apt-get install python serial. And now, to use this code, you simply in your Python code say, after you import the library PySerial, you come and say serial.serial, and then you supply here two arguments: the device, a location of where the device is, and the baud. The baud basically dictates the speed of communication. And then, this will return a handle to the serial module, which you can then use, or the serial object, which you can then use to call serial related functionality. For instance, in the Raspberry Pi, we supply the following arguments: typically serial.serial, and then the location of where the device is under /device/tty AMA0, and then we supply the speed 9600, and this will now give us an object serial that we can then use to communicate. Communicating is super easy. We just say serial.write and then supply the string that we want to communicate to the other device. And if we want to read, then we simply say serial.read, and that will return communication that we receive from the other device. In here, we put it in a loop and we just print it to the screen. I'm going to skip 9.7 because we won't be needing it, and go all the way to 9.8. Now, how do we really make connections? We make connections by taking from the GPIO pins and then connecting them to, let's say, something like a breadboard like this. So for instance, if I want to control this LED, then this LED I connect it to one of my GPIO pin. In here it's GPIO 18, and then I connect the LED itself to a resistor, and then again to the ground. So I form a circuit like this, and now I can go to the Raspberry Pi, write code, and depending on what I put on this pin 18, high or low, this LED will light up. We're going to see this code later on in other chapters, but for now at least we understand how the connection is made. It's really super simple, and there's a connection for every kind of device you want to control. So there is a connection for LEDs, there is a connection for motors, there is a connection, and many of the upcoming chapters are dedicated to showing you the different kind of connections you can do to control different devices. But this is the simplest one. It's for just lighting a simple light, an LED, and it's easy. You connect the GPIO pin to the long leg of the LED. The short leg of the LED is then connected to what we call a resistor to limit the current that I draw from there, and then I connect back to the ground. Now, sometimes making the connections in here is a problem. So what I do is that I simply use, this is called the ribbon cable. I use these 40 pin ribbon cable, and then I kind of like migrate the accessibility of these pins to the breadboard itself. So in here, this is where the breadboard will land, and then I can easily make connections on the breadboard from here. So this just makes it easy to put the wires on the other side. I actually don't prefer it. I prefer the other one. Now, this is, for instance, what, there are many names for what we call hats on the Raspberry Pi. This is one of those hats, and it's called the Raspberry Squid. And what it does here is that it gives you something similar to what we saw earlier in the chapter, the names of the different kind of pins that we have. But then you can then take connections from here. Like for example, here they have, this is what we call an RGB LED, which means it's an LED. It's a light like the one that we've seen before, but we can really control the color of that light. So it connects to 3 different lines, 18, 23, and 24, and then there's a ground connection. So there it's connected. And the code for this is, you can import it a library. It's called for controlling the squid. And you simply define the squid, and then you change its color every time you want to do so, and you can use the time.sleep function in order to wait for some time on that color. So what we notice would happen here is that after I initialize the squid and I have a handle for the object that will control it, then I can use this handle to, let's say, set red, and which means that it will turn red, and then I sleep for 2 seconds, so it will remain red, and then I come back to turn it green, and then I sleep, then blue, then I sleep, then white, then sleep, and so on. So this just typically how things go with the Raspberry Pi is that you get a hat, and the hat has a library so that you can use it. You import that library like we did with the squid here, and then you begin to use the library functionalities or API in order to do the functionality that you really want. Now, the squid also, for instance, gives you the access to connect buttons. So you have that squid button module. So you import the squid button module, you import time, and then you create a button, and you assign that button the pin number where you have hooked it up, and it gives you back a handle, and then you can from that point forward you can come and say B, hey object B, are you pressed or not, and capture that with an if statement to then say whatever you want to say for this. I don't want you to focus too much on the squid, because we're going to be doing things more differently later on. So the squid is more or less simplifies certain connections. Now, if you recall, we said that the Raspberry Pi, when connected to other things, especially the input pins, need not to exceed 3.3 volts. But there are devices that we can connect that might have, for example, a 5-volt output, like in here. Like this device called an Arduino has a 5-volt output. When I turn something on the Arduino, it has 5 volts. When I turn it off, it has 0 volts. The Raspberry Pi is different though. When something goes high or something goes 1, it needs not to exceed 3.3 volts in order to protect it. So what do I do? What I do is that I create a voltage divider. Okay, these two resistors configuration here is called a voltage divider. What happens is I'm gonna connect the line that comes with 5 in here, and I'm gonna connect the ground in here. And notice the ground is also connected in here. So all grounds are connected to the same thing. Here the Raspberry Pi has what we call the ground connection. Okay, one reference point for the entire circuit, and then again this is connected to the ground of the Raspberry Pi, right? Now the output from the Arduino, I'm gonna connect it here, but I'm gonna take the input to the Raspberry Pi to be from this side. Okay, what does that mean? Notice that when I put the input in here, there is 5 volts, but that 5 volts will be divided between the two resistors because of the way that they are connected in series. Whenever I have voltage on resistors that are connected in series like this, then the voltage divides, and the way that it divides is based on the ratio of these numbers that I put in here, the choices of resistors I use. For instance, now, I want to know how much would be the output from here, so it will be 470 divided by their total. So 470 divided by the total of these two will come to be the number that will then be multiplied by the 5 volts. So if I take 470 and I add to it 270, so that will be 540, 740. So if I divide 470 by 740, let's do the math. So I have 270 plus I have 470 and 270. 470 plus 270, that will be the total that I have, and then I'm gonna say the ratio of the resistor is 470, and that's 0.635. So that 0.635, I'm gonna multiply it by 5 volts, comes out as 3.17. That is fine. That's close to the 3.3 volts that I want to go to the Raspberry Pi. So when I put 5 volts in here and then I collect from the top of the 470 resistor, and since the voltage will be divided between these two based on their ratio to the total, then in this case I guarantee that the 5 volts that come in here has come out as 3.3 volts, which then connect to the Raspberry Pi and I can use for whatever purpose I want. There is an easier way of doing this, is that if I buy a module like this, which is called a level shifter or a level converter, this one is easy. Connect the voltage that you want, 5 volt, or you can connect from 1.7 all the way to 5.7 volt. And then you can get the voltage on the output to be programmed to be anything from 1.2 to 3.6. So this is quite convenient. You connect whatever you want from one end, and you can collect whatever you want from the other end. So this allows you to make the connections without having to use resistors or voltage dividers. The price of doing so is that it's more expensive compared to, for example, like using just simply two resistors to fix this problem. Now, this upcoming recipe is extremely important, where what we will do is that we're going to look at how we can power the Raspberry Pi using batteries. So this circuit is of extreme importance, so pay attention. What I want to do now is, I don't want the Raspberry Pi to be connected to a USB port, to a computer, or to a laptop. I want to connect it to batteries so that I can move it around or place it wherever I want. So in order to do this, I know that I need 5 volts to be connected to the Raspberry Pi to power it, and not any less than 5 volts. If you remember the principles that we have looked at the beginning of the chapter, which tells me how to power the Raspberry Pi, or how to maintain the Raspberry Pi and not destroy it. So what I do here is that each one of these AA batteries is 1.5 volts, but the way that they are connected here is in series. So 1.5 volts, the end of one is connected to the beginning of the other one. That's a series connection. Again, 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 and again. Now when I look at the total of this, so I have 1.5, and then I have 1, 2, so that's 3 volts, 3 volts, 3 volts, so that's a total of 9 volts. So this battery can power the Raspberry Pi, but the problem with this 9 volt battery is that it's more than the 5 volt that the Raspberry Pi requires in order to power. So notice here, to power the Raspberry Pi, I need to connect to the 5 volt pins that are on the Raspberry Pi from these batteries, but these give out a total of 9 volts. So what I do is that I use this device. This device is called the regulator, and it has 2 legs to put the inputs and 2 legs to take the output. Now the legs that are in the input, I'm going to connect it to the batteries. So one end of the battery from here, and then this end of the battery from here. So the input pins, which are the ones to the left and center, these are going to be called the input pins. The output pins are the center and the right. Notice that the center is joint, or is common between them, because it's the ground. So what I do is that I connect the ground to the ground. That's the common point in the circuit that gives me a reference point against which I can test all of the other voltages. And then in here, I'm going to connect the input from the batteries. Okay, and then the output from this regulator I'm gonna connect to the Raspberry Pi. The regulator is kind of like a guard. What it does is that it sees the input and then makes sure that whatever the output is matches whatever value you buy it for. So for example, if you buy a 5-volt regulator, that means you are guaranteed that the output of the regulator will be 5 volt. Okay, if you buy a 6-volt regulator, it means you can connect anything higher in the input than 6 volts, but the output will be 6 volts. If you buy a 9-volt regulator, that means you can connect in the input anything higher than a 9 volt, but the output will be a 9 volt. But where is this excess energy going? If you notice, there is a metal part here, and that metal part will heat up. Regulators will heat up, and the metal part heating up is a way to dissipate this excess energy. So this will then just basically turn into heat, and that heat will dissipate into the air, and it won't cause any damage. So in here we put a 9 volts coming in, and then the output from this is 5 volts, which is what the Raspberry Pi wants. Now I'm gonna put a these are called capacitors. As you can see, their values in, let's say, 100 microfarad and 100 nanofarad, and I'm going to connect the 100 microfarad capacitor 2 into the output side, the input side, and then I'm going to connect the 100 nanofarad capacitor into the input side, and that will help me also filter any variations in the signals and clean it up. So this is how I power the Raspberry Pi with a number of AA batteries. Now, if I don't want that mess of a circuit involving the regulator and the 2 capacitors, what I can do is that I can get a Pi robot board. The Pi robot board already has all of these capacitors and regulator and everything, and I can simply just use this battery back and connect it directly to the board, and then the board itself will power the Raspberry Pi. This hat, the Raspberry Robot Hat, will then power the Raspberry Pi. Now the thing is with the Raspberry Robot Hat is that it has other functionalities that can be used for robotics, not necessarily only the ability to have a power supply circuit that feeds the Raspberry Pi. So there could be other uses for it that you'd find in your project. Now, you could also power the Raspberry Pi from a LiPo battery. These are the same kind of batteries that you used to have in mobile phones when you used to be able to change or replace your LiPo battery. The problem with these batteries is that they give a 3.7 volt only, and we need 5 volts to power the Raspberry Pi. It's the opposite of the problem we had earlier. In the problem we had earlier, we were getting 9 volts, and we were stepping that down to 5 volts in order to feed the Raspberry Pi. In here, it's the opposite. We have a 3.7 volt battery, and we want to step it up to 5 volts. In order to step it up, we have this circuit there, okay, and this module, which you can buy, will do 2 things. Will give you power indicators, will give you the ability to hook up a charger. So from this end, you can hook up a USB cable and charge the battery directly. So it has a charging circuit on board. It has LEDs to tell you when it's charging and when it's on. And at the same time, it will have a booster. And the booster will take the 3.3 volts and then boost it up to 5 volts, which can then power the Raspberry Pi. Another very famous hat that we will eventually come to use later on in the chapters is called the Sense Hat. And the Sense Hat is really special. So this is the Sense Hat. It sits on top of the Raspberry Pi, and it allows you a number of interesting sensors. For example, it has a temperature sensor, it has a humidity sensor, it has a pressure sensor, it has an accelerometer, gyroscope, and magnetometer, which are called 9 degrees of freedom motion sensors. It has this joystick which you can use to interact with the Raspberry Pi or the hat, and then it has this lid matrix, and it's a full RGB lid matrix that allows you to draw on the Raspberry Pi or to communicate with the user simple messages. It comes with a library that allows you to read all of the values of these sensors, as well as to control the LED or to read from the joystick. So it's really interesting. To install this library, you simply say sudo apt-get install sensehat. There is another library for image processing. It's called the Python Image Library, or PIL, and you can install this again with sudo pip install pillow. And once you do this, you can then, let's say I want to import the sense hat from the sense hat module, create an object for it, which is by calling the constructor sense hat and keeping the reference to it, so hat. And then if you want to show a particular message, for example, on the LED matrix, you can say hat dot show message and pass the string that you want, and what will happen is that this message will slide or will scroll on the LED, allowing on the LED matrix, allowing the user to see it. That's one use of the hat. We will have other recipes in the future, like we mentioned here, that will be more interesting, and which is ones that we'll use in order to read the sensor values of the Raspberry Pi and see how we can work with it. There is a new hat also called the Explorer hat. This hat is really simple. It's there for basically hobbyists and those who come from an Arduino background. It gives you a number of things. For example, it gives you 4 LEDs. It gives you 4 buffered inputs, 4 buffered outputs, which boost on top of what the Raspberry Pi can give you. Notice you can have up to 500 milliampere powered by those. It has 4 analog inputs. This is something that the Raspberry Pi did not have. So instead of giving your own analog digital converter later, as we will do, this one will give you 4 inputs that are analog. It has 2 low power motor drivers, but a maximum of 200 milliampere, so you can connect simple motors to them. It has 4 capacitive touch pads, and it has 4 capacitive crocodile clip pads. So there are multi ways you can interact with this. For example, in here, these pads are called the capacitive touchpad. I'm going to show you what you can do with those later on. You can hook it up to an object, let's say like a banana or an apple, and then detect when somebody touches them. So this is called capacitive touch. And you can connect them with crocodile clip pads, and these are, you're gonna see those in the lab. There's a little bit of a prototyping area. So this simple system allows you then to control simple motors, to have a little bit of analog input and so on. So it's good for hobbyists and those who are starters or kids learning in schools and so on. Notice here also that it groups for you. It makes it easy for you to get the pins that are related to serial communication protocols. Like for example, the I2C pins are easily marked and available on this side, the serial pin on this side, the SPI pins on this side, and there's a 3.3 volt there and a PWM. So it also kind of organizes the Raspberry Pi for you, so that it puts the pins that go together next to each other, making the connections easier for kids and others. Now we discussed this Raspberry Robot hat, and Raspberry Robot hat is one that connects to the Raspberry Pi. Again, there is a procedure here to install and set it up. Once you do this, you can then import the library and you can create an object. Here, for example, we're going to say RRB3 and then create an object, and then we can use these objects to do whatever we need to control the hat. For example, we can say rr.setLED11 or setLED10. We can check if a switch is closed or not. So typically hats come with libraries that makes it easy for the user to control them, but we look for a more advanced approach to doing so, so we'll be able to do our own a little bit into the future. Another one is called the Pi plate prototyping board. This is again sits on top of the Raspberry Pi. The difference there is that's not a breadboard, so connections that you do here are pretty much permanent and involve soldering. So this is like a breadboard that you solder, and that makes the wires not loose and can simply be disconnected easily, which gives it a more permanent solution to your circuit needs than, let's say, a breadboard, which you can use for prototyping. So for instance, here I can make the connections to the ground. This is the same connection that we had before for the RGB LED. We can make a connection to the ground. We can make the connections to the 3 different pins that we have in here in order to ensure that these pins are connected to the RGB LED, and then we can connect the RGB LED. Notice that all of the connections then from the other end are soldered. It doesn't look like it from here, but from the other end what you do is that you solder in order to make sure that these connections are permanent. And it's more tidy than having a breadboard, and also they do again try to group for you pins that you will often need to connect together. So this is the soldering part. This is how we flip it from the other side and ensure that, for example, these are the 2 legs of the resistor, and what we will do is that we will solder to ensure that this is a permanent connection, then cut the extras, and that will give us a more robust circuit to work with here. So for example, notice these are the three resistors, and from the back end we have these are the three soldering marks that are there to keep the legs of the resistors in the right place. Of course, we cut the extras, and now this connection is much more of a robust connection than the other one. That will be the end product. There is a Perma Proto. So this one is also proto board, but it's a smaller proto board. Sometimes that's all what you would need. There is a more advanced module here called the compute module, and what that does is that it allows you to expand the RAM of the Raspberry Pi. It increases its processing power. You can use this if what you want the Raspberry Pi to use is more advanced than what features it supplies you, from the get-go. There is a Raspberry Pi called the Raspberry Pi Zero, and that Raspberry Pi Zero is a smaller Raspberry Pi. It's less capable than the one that we know, but it's half of the size. And it's quite interesting because that device becomes really, really small, half of a credit card size, but can still run all functionality of Linux, which makes it a very powerful device. And you can use that for your IoT projects. It's really, really awesome because our Raspberry Pi is the card is impressive. It's the size of a credit card. This one is even more impressive because it's smaller. The drawback is that this does not have the same RAM and processing power as the Raspberry Pi has, but sometimes this is more than what you would need, really.